Good afternoon. Now we are going to see the next section of the real analysis, say Riemann-Stieltjes integral. So here we recall from elementary calculus to find the area of the region under the graph of a positive function f defined on the closed interval a comma b. We subdivide the interval a comma b into a finite number of subintervals, say n, the kth subinterval having the length delta xk, and we consider the sums of the form summation of k varies from 1 to n f of tk into delta xk, where tk is some point in the kth subinterval having length. Such a sum is an approximation to the area by means of rectangles. Integral f dx, which is properly known as the Riemann integral, where f is a continuous function on the bounded in the closed interval a comma b. So usually we use it to denote this Riemann integral as integral a to b f dx. So here we are going to see the definitions and some notations of Riemann-Stieltjes integral, linear properties, integration by parts, change of variable in a Riemann-Stieltjes integral, step function as integrators, reduction to a Riemann-Stieltjes to a finite sum, Euler's summation formula, and monotonically increasing integrators, upper and lower integrals, Riemann's condition, comparison theorems, integrators of bounded variation, sufficient condition for the existence of Riemann-Stieltjes integrals, and similarly necessary conditions for the existence of Riemann-Stieltjes integrals. First, the notation for the Riemann integral. Integral a to b f dx, we use it to denote for Riemann integral, which is defined as the limit of the sum of f of tk into delta xk, where tk is an interior point in the kth subinterval having the length delta xk. Now we consider more general concept of Riemann integral, namely Riemann-Stieltjes integral. For that, we consider a partition P of the closed interval a comma b as a finite set of points from a to b. A partition P of P dash of a comma b is said to be finer than P if P is a subset of P dash or P dash is a superset of P. Here P is the length of the subinterval of P. The length of the subinterval we use it to denote it by norm of P, and obviously norm P less than or equal to norm P. So as we take finer and finer partition, the norms goes on decreasing. Next one, alpha is a function of x. P is a partition consisting of the points from a to b. The points are from x0, x1, etc., xn, and the kth subinterval as the closed interval xk minus 1 comma xk. Delta alpha k stands for alpha of xk minus alpha of xk minus 1. So if you put k values as 1, 2, 3, we can get the respective one, and similarly if k equal to n, then delta alpha n is alpha of xn minus alpha of xn minus 1. Therefore summation of f of tk into delta alpha k is nothing but alpha of b minus alpha of a, where a and b are the endpoints of the partition P of a comma b, and this P of a comma b denotes the set of all possible partitions on the given interval, closed interval a comma b. So next definition for Riemann-Stieltjes integral. Riemann-Stieltjes integral f and alpha are the two functions of x. Let P be a partition from x0 to xn in the closed interval a comma b, and tk be a point in the subinterval xk minus 1 comma xk. A sum of the form Sp f alpha equal to summation of k varies from 1 to n f of tk into delta alpha k. That is, Sp f alpha can be expressed as sum of f of tk into, instead of delta alpha k, here we can write it as alpha of xk minus 1 minus alpha of xk, and this we call it as the Riemann-Stieltjes sum of f with respect to alpha. This we in short we use it to write it as Sp f alpha, that is Riemann-Stieltjes sum of the partition P of the function f with respect to alpha. So we say that f is Riemann integrable with respect to alpha on the closed interval a comma b. Simply we use it to write f belongs to R of alpha on the closed interval a comma b. If there exists a number a having the following property, we can write for every epsilon greater than 0, there exists a partition P epsilon of a comma b, such that for every partition P finer than P epsilon, and for every choice of the point tk in the closed interval xk minus 1 comma xk, we have modulus of SP f alpha minus A is less than epsilon. When such a number A exists, it is uniquely determined and it is denoted by integral A to B f d alpha, that is A equal to integral A to B f d alpha, or otherwise we use it to denote this as integral A to B f of x into d alpha of x. We also say that the Riemann-Stieltjes integral A to B f d alpha exists, or simply we use it to write f belongs to R of alpha. Here the functions f and alpha are referred to as the integrand and the integrator, that is f is an integrand and alpha is the integrator respectively. Some other notations are there exist, for every, and such that for Riemann-Stieltjes integral we use it to denote it as RS integral. From the definition of the Riemann-Stieltjes integral, as a special case, if alpha of x is equal to x, then we use it to write integral A to B f of x into d alpha of x as integral A to B f of x into dx. Here integral A to B f of x into dx is called the Riemann integral. Thus, Riemann-Stieltjes integral becomes a Riemann integral whenever alpha of x is equal to x. We also write SPF instead of SPF alpha and f belongs to R instead of f belongs to R of alpha. Next definition for a Riemann-Stieltjes integral. Let P be a partition of the closed interval a comma b, and by definition SP f alpha can be written as summation of f of tk into delta alpha k, which is called the Riemann-Stieltjes sum of f with respect to alpha, and here tk belongs to the closed interval xk minus 1 comma xk. If there exists a number a such that SP f alpha minus a, as p becomes finer and finer, then the integral a can be expressed as integral A to B f d alpha. Here is an example for the Riemann-Stieltjes sum integral 0 to 2 x into d of x, and the SP f alpha we have obtained in the form summation of f of tk into alpha of xk minus alpha of xk minus 1. So, based on this we use it to write the values as f of 0 into a of 1 by n minus a alpha of 0 etc., and finally here we get 2 minus 1 by n, that is SP f alpha tends to 2 as n tends to infinity. Another one example for the same Riemann integral process and the linear properties. So, first one, if f belongs to R of alpha and if g belongs to R of alpha on the closed interval a comma b, then C1f plus C2g belongs to R of alpha on the closed interval a comma b for any two constants C1 and C2. We have integral a to b C1f plus C2g of d alpha equal to C1 integral a to b f d alpha plus C2 integral a to b f d alpha. So, to prove this, let us take h as C1f plus C2g, and for any partition P on the closed interval a comma b, we have h of tk equal to C1 into f of tk plus C2 into g of tk, where tk belongs to the closed interval xk minus 1 comma xk. So, based on the definition of Riemann-Stieltjes integral, we can write using h, that is SP h alpha can be expressed as sum of h of tk into delta alpha k, and h of tk as it is, instead of delta alpha k we can write alpha of xk minus alpha of xk minus 1, and here it is C1 f of tk plus C2 into g of tk instead of h into alpha of xk minus alpha of xk minus 1, that is sum of C1 f of tk into alpha of xk minus alpha of xk minus 1 plus C2 into g of tk into alpha of xk minus alpha of xk minus 1, which is nothing but C1 into SP f alpha plus C2 into SP g alpha. Let us suppose that integral a to b f d alpha equal to a, where f belongs to R of alpha. Since f belongs to R of alpha implies that a exists and also it is unique. So, instead of a we can use it to write integral a to b f d alpha. So, therefore, by the definition, for any given epsilon greater than 0, there exists a partition P dash belongs to A comma B, where P is contains P dash, such that modulus of SP F alpha minus A is less than epsilon. Similarly, we can write for G and B exists and also it is unique. Therefore, by the definition, for a given epsilon greater than 0, there exists a partition P double dash belongs to closed interval A comma B, such that modulus of SP G alpha minus B is less than epsilon. Hence, we can take P epsilon is a union of P epsilon dash union P epsilon double dash for any partition P finer than P epsilon. Thus, we have modulus of SP H alpha minus C1 of integral F d alpha minus C2 of integral G d alpha is nothing but C1 modulus of C1 SP F alpha minus C1 integral F d alpha plus C2 SP G alpha minus integral G d alpha. So, if we simplifying this, we get which is less than some epsilon 1 or epsilon. Hence, the left hand side LHS is less than epsilon, and this implies that SP H alpha tends to C1 integral A to B F d alpha plus C2 integral A to B G d alpha. Therefore, for all the partitions of P, we can write integral A to B C1F plus C2G of d alpha is equal to C1 of integral A to B F d alpha plus C2 of integral A to B G d alpha. So, in this, if C1 is equal to C2, we can obtain the above expression will becomes integral A to B F plus G d alpha equal to integral A to B F d alpha plus integral A to B F d beta, that is F belongs to R of alpha and G belongs to R of beta, and hence F plus G belongs to R of alpha. Theorem 2 states that if F belongs to R of alpha and F belongs to R of beta on the closed interval A comma B for any two constants C1 and C2, then F belongs to R of C1 alpha plus C2 beta. Then we have integral A to B F d of C1 alpha plus C2 beta equals C1 integral F d alpha plus C2 of integral F d beta. Again here let us consider H as C1 alpha plus C2 beta, and by proving the above, similarly here we consider SP F comma H, and that can be written as summation of F of Tk into delta Hk. That is summation of F of Tk into, instead of delta Hk we can write H of xk minus H of xk minus 1, and Tk is an interior point in the kth subinterval. So, instead of H we can use it to write C1 alpha plus C2 beta, and proceeding in the same way above we get C1 SPFH plus C2 SPFH. So, now we consider the modulus of SPH minus C1 integral F d alpha minus C2 integral F d beta, and that is less than or equal to epsilon by using the above definition. So, hence integral A to B F d of C1 alpha plus C2 beta is nothing but C1 of integral A to B F d alpha plus C2 of integral A to B F d beta. Assume that C belongs to open interval A comma B if two of the three integrals, integral A to B F d alpha plus integral C to B F d alpha, integral A to B F d alpha exist, then the third also exists. So, here three different integrals are given. So, if any two of the integrals exist, then the third also exists, and the third one can be expressed as the sum of the remaining two. So, to prove this, we consider a partition P of the closed interval A comma B such that C belongs to P, and let us consider P is the union of P1 union P double dash. That is, P dash is the partition of the closed interval A comma C, and P double dash is the partition of C comma B. Now, let us assume that integral A to C F d alpha plus integral C to B F d alpha exist. Now, we want to show that the sum of these two is nothing but integral A to B F d alpha. So, by the definition of Riemann-Stieltjes integral, Given epsilon greater than 0, there exists a partition P epsilon dash of A comma C such that modulus of S P dash F alpha minus integral A to C F d alpha is less than epsilon by 2 whenever P dash is finer than P epsilon dash. Similarly, we can write for P epsilon double dash and for the partition of C comma B. So, now we consider modulus of SP F alpha minus integral A to C F d alpha minus integral A to B F d alpha equal to modulus of SP dash F alpha plus SP double dash F alpha minus of the two integrals. So, this is less than epsilon and hence we get modulus of SP F alpha minus integral A to C F d alpha minus integral C to B F d alpha is less than epsilon and hence integral A to B F d alpha also exists, and thus integral A to B F d alpha is nothing but the sum of the integral A to C plus C to B. If we consider 2 points A and B, if A less than B, we define the integral as integral A to B F d alpha equal to minus of integral B to A F d alpha whenever integral A to B F d alpha exists. Also, integral A to A F d alpha is 0. So, here it is given that integral A to A F d alpha equal to 0, and from the above definition integral A to B F d alpha is nothing but minus of integral B to A F d alpha. Next section, integration by parts. A remarkable connection exists between the integrand and the integrator in Riemann-Stieltjes integral. The existence of integral A to B F d alpha implies the existence of integral A to B alpha into df, and the converse is also true. Moreover, a very simple relation holds between the two integrals. We exhibit the relation in the form of a theorem that we know as integration by parts, and this relation is called the reciprocity law for the integral, or also we can call this as a formula for integration by parts. If f belongs to R of alpha on the closed interval a comma b, then alpha belongs to R of f on closed interval a comma b. Then we have integral a to b f of x into d alpha of x plus integral a to b alpha of x into d f of x equal to f of b alpha of b minus f of a into alpha of a. So, the above expression that we call it as the formula for integration by parts, or otherwise it is known as the reciprocity law for the integral. To prove the above integral, let epsilon greater than 0 be given, and since integral a to b f d alpha exists, because by the given data f belongs to R of alpha on closed interval a comma b. So, by the definition, whenever f belongs to R of alpha, then integral a to b f d alpha exists. Similarly, alpha belongs to R of f also given, and hence integral a to b alpha df also exists. So, now we are going to consider the partition for these two integral. In the first case, integral a to b f d alpha exists, and we consider a partition say p epsilon of the closed interval a comma b, such that for every partition p1 finer than p epsilon, we have modulus of sp1 f alpha minus integral a to b f d alpha is less than epsilon. So, consider the Riemann-Stieltjes sum for the above integral, integral a to b alpha df. We used to write sp alpha f as summation of alpha of tk into delta fk. That is, this is nothing but summation of alpha of tk into f of xk minus f of xk minus 1, and tk belongs to the closed interval xk minus 1 comma xk. Here p is finer than p epsilon. Now, let us define a as a equal to sum of f of xk into alpha of xk minus sum of f of xk minus 1 into alpha of xk minus 1. That is nothing but f of xn into alpha of xn minus f of x naught into alpha of x naught. Therefore, a can be written as f of b into alpha of b minus f of a into alpha of a. From the equation 2, we can write Sp alpha f can be expressed as sum of alpha of tk into f of xk minus alpha of tk into f of xk minus 1. Now from 3 we subtract equation 4, we get the equation in the form a minus Sp alpha f equal to summation of xk into alpha of xk minus alpha of tk plus summation of f of xk minus 1 into alpha of tk minus alpha of xk minus 1. So in this above equation, the right hand side of equation 5, we have the two sums and so can be combined into a single sum of the form S P1 F alpha, and P1 is a partition of a comma b obtained by taking the points xk and tk together. Then P1 is finer than P and hence finer than P epsilon. Thus A minus Sp alpha f equal to summation of first case will become 0 and f of xk minus 1 into alpha of tk minus alpha of xk minus 1, and thus A minus Sp alpha f can be expressed as insets, and hence the Riemann-Stieltjes sum for f with respect to alpha can be expressed above, that is modulus of A minus Sp alpha f minus integral a to b f d alpha is less than epsilon for all the partitions p finer than p epsilon. So this implies that integral a to b alpha df exists, and therefore integral a to b alpha df is nothing but a minus of integral a to b f d alpha, and thus by combining these two we can get integral a to b alpha df plus integral a to b f d alpha equal to a. Already by the definition of a is nothing but f of b alpha of b minus f of a alpha of a. So based on the formula for integration by parts, here we give an example. And the next section, change of variable in a Riemann-Stieltjes integral. Let f belongs to R of alpha on closed interval a comma b, and let g be a strictly monotonic continuous function defined on an interval S having endpoints c and d. Assume that a equal to g of c and b equal to g of d. Let h and beta be the composite functions defined as follows: h of x as f of g of x and beta of x as alpha of g of x for every x belongs to S. Then we have to show that h belongs to R of beta on S, and we have integral a to b f d alpha is nothing but integral a to b f d beta. That is integral, instead of a and b we use it to write g of b to g of d, f of t into d alpha of t equal to integral c to d f of g of x into d of alpha of g of x. So now let us define g is a strictly increasing function on the given interval S. Also let us assume c less than d. So since g is a strictly increasing continuous function, then g inverse also exists on the given interval. So thus g is 1 to 1 and it has a strictly increasing continuous inverse g inverse defined on a comma b. Then we consider a partition P for the inverse function that we named as y0, y1 etc. yn of the closed interval c comma d, and there corresponds one and only one partition, say P dash, which is nothing but x0 to xn of the closed interval a comma b, with a condition that xk is equal to g of yk. Therefore in general we use it to write the partition as g of p equal to p1. Further, a refinement of p produces a corresponding refinement of p1 and vice versa. Therefore g of p is p1 and g inverse of p1 equal to p. So since here f belongs to R of alpha, f is Riemann integrable, so integral a to b f d alpha exists in this. Therefore by definition, given epsilon greater than 0 and there exists a partition p epsilon 1 of a comma b such that p1 is finer than p epsilon 1, and hence modulus of s p1 f alpha minus integral a to b f d alpha is less than epsilon. Let us consider the partition p epsilon as g inverse of p epsilon dash, which is the corresponding partition of the closed interval c comma d. Let p varies from, that is p from y0 to yn which is a partition of the closed interval c comma d finer than p epsilon. Now we consider the Riemann-Stieltjes sum SP h beta, that is SP h beta is summation of h of uk into delta beta, where uk belongs to the closed interval yk minus 1 comma yk and delta beta k equal to beta of yk minus beta of yk minus 1. If you put g of uk and xk as g of yk, then the partition P1 is from x0 to xn, which is a partition of the closed interval a comma b finer than p epsilon 1. Therefore, SP h beta equal to sum of f of g of uk into alpha of g of yk minus alpha of g of yk minus 1, and this is nothing but f of tk, that is summation of f of tk into alpha of xk minus alpha of xk minus 1. Since the right hand side of the Riemann-Stieltjes sum of f with respect to the partition P1 on the given closed interval a comma b for the partition P1 of a comma b, and tk is the interior point of the kth subinterval, and hence SP h beta, that is the Riemann-Stieltjes sum of the partition P with respect to h equal to SP1 f alpha. Therefore, this we can express as modulus of SP h beta minus integral a to b f d alpha is less than epsilon, that is integral a to b f d alpha equal to integral a to b h into d beta, or here a equal to g of c and b as g of d. So, we use it to write integral g of c to g of d, f of t into d alpha of t can be expressed as integral c to d f of g of x into d of alpha of g of x. The next theorem states that the reduction of a Riemann-Stieltjes integral to a Riemann integral. Already we have seen that whenever alpha of x is equal to x, then we can say that the Riemann-Stieltjes integral will become Riemann integral. So, here assume f belongs to R of alpha on the closed interval a comma b, and assume that alpha has a continuous derivative alpha dash on the closed interval a comma b. Then the Riemann integral a to b f of x into alpha of x dx exists, and we have integral a to b f of x into d alpha of x can be expressed as integral a to b f of x into alpha dash of x into dx. So, instead of d into alpha of x, we can write alpha dash of x into dx. Here this remark tells us that we are permitted to replace the symbol d alpha of x by alpha of x into dx in the given integral a to b f of x into d alpha of x whenever alpha has a continuous derivative alpha dash. So, now let us consider the function g of x, and that is nothing but f of x into alpha dash of x. Consider the Riemann sum SPG equal to SPG of beta, where beta equal to x. That means here SPG used to denote the Riemann integral, that is SPG equal to sum of k varies from 1 to n g of tk into delta xk. Here tk is the interior point in the kth subinterval, and this is equal to summation of f of tk into alpha dash of tk into delta xk by using the above equation 1. So, the same partition P and the same choice of the point tk, which can be used to form the Riemann-Stieltjes sum Sp f alpha as f of tk into delta alpha k. Now, we are applying the mean value theorem. We can write delta of alpha k as alpha dash of Vk into delta xk. Since mean value theorem states that f dash of c as f of b minus f of a divided by b minus a, here c is Vk and b is xk and so on. So, based on this, we used to write alpha dash of Vk into xk minus xk minus 1 is equal to alpha of xk minus alpha of xk minus 1, or otherwise alpha dash of Vk into delta xk is equal to delta alpha k. Thus, Sp f alpha can be expressed as summation of f of tk into alpha dash of vk into delta xk. This is from 3 in equation 2. So, similarly the equation b minus a, that is sp f alpha minus sp g, can be expressed as summation of f of tk into alpha dash of vk minus alpha dash of tk into delta xk. So, since f is bounded, so we can write modulus of f of x is less than or equal to m for every x belongs to the interval where m is greater than 0. Also, given that alpha dash is continuous on the closed interval a comma b, that implies uniform continuity of alpha dash on the closed interval a comma b. Thus, if delta greater than 0 and for any epsilon greater than 0, depending only on epsilon, such that modulus of x minus y is less than delta, that implies modulus of alpha dash of x minus alpha dash of y is less than epsilon by 2 m of b minus a. If we consider a partition p epsilon dash with the norm p epsilon dash norm is less than delta, and for any finer partition p, we have modulus of alpha dash of vk minus alpha dash of tk is less than epsilon by 2 m of b minus a. For such partitions, from the expression c, we used to write modulus of sp f alpha minus sp g is nothing but sum of f of tk into alpha dash of vk minus alpha dash of tk into delta xk. So, this is less than or equal to summation of modulus of f of tk into modulus of alpha dash of vk minus alpha dash of tk into modulus of del xk. Now, we are applying the above expression in this, finally we use it to get epsilon by 2. Thus, modulus of sp f alpha minus sp g is less than epsilon by 2. Also, f belongs to R of alpha on the closed interval a comma b, then there exists a partition p epsilon double dash such that for any p finer than p epsilon double dash, we can write modulus of sp f alpha minus integral f d alpha is less than epsilon by 2. So, now we consider the same for g also, that is spg minus integral f d alpha. Again we consider a partition say p epsilon, and that is nothing but p epsilon dash union p epsilon double dash. We can write modulus of sp f alpha minus integral a to b f d alpha is less than epsilon, and hence integral a to b f d alpha exists, that is integral a to b f of x into d alpha of x. By rearranging this above, we can get the required form, that is since we know that a equal to f of b alpha of b minus f of a alpha of a, and hence we obtain the required form. The next one, step function as integrators. So, the function the graphical representation for the step function is given here, and the problem based on the above, that is if a comma b, in between a and b, yes we consider, and f is bounded on a comma b. Also we say that f is continuous at s and alpha of x is equal to 0, where x is less than or equal to s, then we have to show that integral a to b f d alpha equal to f of s. So, by using the above value, we can prove the required form. Since sp f alpha is nothing but the Riemann-Stieltjes sum of f with respect to alpha, that is nothing but summation of f of tk into alpha of xk minus alpha of xk minus 1, and we can use f of tk into alpha of xk, that is 1 minus 0, and hence we have obtained f of tk which tends to f of s. Thus, f is continuous at s, and hence the value of the Riemann-Stieltjes integral is nothing but f of s. Similarly, the another one example given for the same. And this theorem based on the above right hand and the left hand derivative, given a less than c less than p, define alpha on the closed interval a comma b as follows. The values alpha of a, alpha of b, alpha of c are all arbitrary, and alpha of x is equal to alpha of a if a less than or equal to x less than c, and alpha of x is equal to alpha of b if c less than x less than or equal to b. Let f be defined on the closed interval a comma b in such a way that at least one of the functions f or alpha is continuous from the left at C and at least one is continuous from the right at C. Then f belongs to R of alpha on the closed interval a comma b, and we have integral a to b f d alpha equal to f of c into alpha of c plus minus alpha of c minus. So, here the pictorial representation is given for the right hand derivative and the left hand derivative for both f and also alpha. So, to prove the above, if C belongs to P, every term in the Riemann-Stieltjes sum, say sum SP f alpha is 0, except the two terms arising from the subinterval separated by C. So, we are assuming this, if C belongs to P in the given partition P, except the two subintervals separated by C, all the other terms are 0. That is, SP f alpha equal to summation of f of t k into delta alpha k, and this can be written as alpha of t k minus alpha of t k minus 1, and we use it to write the endpoints f of t1 into alpha of x1 minus alpha of x0 and so on. And here finally we have obtained that f of t k minus 1 into alpha of c minus alpha of c minus plus f of t k into alpha of c plus minus alpha of c. Since as per our assumption, except these 2 points, all the other terms become 0. So, therefore, equation 1 can be written as delta equal to f of t k minus 1 minus f of c into alpha of c minus alpha of c minus plus f of c into alpha of c plus minus alpha of c, and hence delta is expressed as A. Since f is continuous at C, then by definition for any epsilon greater than 0, there exists a delta greater than 0 such that num of P less than delta and modulus of f of t k minus f of c is less than epsilon, and modulus of f of t k minus f of c is less than some delta. So, thus by using the equation 2, modulus of delta is less than or equal to epsilon into modulus of alpha of c minus alpha of c minus plus epsilon into modulus of alpha of c plus minus alpha of c. So, from the inequality 3, so it holds good that f is, whether it is continuous or not, we can obtain the required form. And here is an example given for both the right and the left hand derivative arising at C. And here the reduction to a Riemann-Stieltjes integral. In this, a function step function can be expressed as a function alpha, which is defined on the closed interval a comma b, is said to be a step function if there is a partition a equal to x naught less than x1 etc., xn equal to b, such that alpha is a constant on each open subinterval xk minus 1 comma xk. Then the number alpha of xk plus minus alpha of xk minus is called the jump of f at xk if 1 less than k less than n. That is, the jump at x1 is alpha of x1 plus minus alpha of x1, and similarly the jump of the function alpha at the point xn is denoted by alpha of xn minus alpha of xn minus. That is, the difference between the right hand and the left hand derivative, we call it as a jump of the function. So, here we are having an example for the jump of the function. Next one, definition for greatest integer function. Its value at x is the greatest integer which is less than or equal to x and is denoted by x. Thus, x is the unique integer satisfying the inequalities, and one of the simplest step functions is the greatest integer function. Since step functions provide the connecting link between the Riemann-Stieltjes integral and a finite sum. So, the following theorem states the above relation. Let alpha be a step function defined on the closed interval a comma b with the jump alpha k at xk, where x1, x2, etc., xn are described in the definition of step function. Let f be defined on the closed interval a comma b in such a way that both f and alpha are discontinuous from the right or from the left at each x naught. Then integral a to b f d alpha exists, and we have integral a to b f of x into d alpha of x equal to sum of f of xk into alpha of k. So, already we have proved the same in theorem 1. So, based on this, we can say that whenever integral a to b f d alpha exists, then we use it to write integral a to b f d alpha is nothing but f of c into alpha of c plus minus alpha of c minus. So, hence we can obtain the required form easily based on the above theorem. Next theorem states that it holds only for the discontinuity at C, and we apply the theorem 1 for all the set of discontinuities in the given interval a comma b. Then we get integral a to b f d alpha as f of x1 into alpha of x1 plus minus alpha of x1 minus plus f of x2 into alpha of x2 plus minus alpha of x2 minus etc. plus f of xn into alpha of xn plus minus alpha of xn minus. So, this also proved in the same way as above. Next, we are having every finite sum can be written as a Riemann-Stieltjes integral. In fact, a given sum of alpha k define f on the closed interval 0 comma n as follows: f of x equal to alpha k if k varies from minus 1 less than x less than or equal to k, and f of 0 equal to 0. Then summation of alpha k equal to summation of f of x f of k, that is nothing but integral 0 to n f of x into d of x, where x is the greatest integer less than or equal to x. Here is a proof for the above one: f of x equal to a k, where k minus 1 less than x less than or equal to k, also f of 0 is 0. So, if it is 0, then there is nothing to prove, and f of x equal to a1, here x lies in between 0 and 1, and similarly going on. Then this function f is continuous from the left as an integer from 1 to n, and since f of 1 equal to a and f of 1 equal to a1 and alpha equal to x, which is continuous from the right and having the jump at each integer. Here it is an example for the jump at the right and the left hand side jump and so on, and the partition for the above one. Euler's summation formula. So, here Euler's summation formula states that if f has a continuous derivative f dash on the closed interval a comma b, then we have summation of f of n as integral a to b f of x dx plus integral a to b f dash of x into dx plus f of a minus f of b, where x is equal to x minus of x when a and b are integers, and this becomes summation of f of n equal to integral a to b f of x plus integral a to b f dash of x into x minus of x plus 1 by 2 into dx plus f of a plus f of b divided by 2. Here summation of f of n gives the sum from n equal to a plus 1 to b. Using the reciprocity law for the Riemann-Stieltjes integral, that is formula for integration by parts, we can write integral a to b f of x into d alpha of x plus integral alpha of x into d f of x equal to f of b alpha of b minus f of a into alpha of a. In equation 1, we replace alpha of x by x minus of x, and we obtain the equation in the form 2, that is integral f of x dx minus of integral a to b f of x into d of x plus integral a to b x minus of x into f dash of x dx equal to f of b into b minus of b minus f of a into a minus of a. Here x has unit jumps at the integral values a plus 1, a plus 2 etc., and therefore by a theorem we can write integral a to b f of x dx as summation of f of n. Now, we substitute this in the equation 2, we can write f of x, that is integral a to b f of x dx minus summation of f of n plus integral a to b x minus of x into f dash of x dx equal to f of b minus of f of a into a minus of a. Thus, the above expression will become summation of f of n is equal to integral a to b f of x dx plus integral a to b f dash of x into dx plus f of a minus f of b. Hence, this is the required Euler summation. And the second half of the theorem here given as a corollary, and the proof is given. So, next is section upper and lower sums of the given partition. So, already alpha is increasing on the given interval. Since we see the increasing functions on the closed interval a comma b, here alpha is increasing, then delta alpha k can be expressed as alpha of xk minus alpha of xk minus 1 in the Riemann-Stieltjes sum are all non-negative. We use it to write alpha increasing on the closed interval a comma b, and by assuming alpha as an increasing function on a comma b. So, we give another definition for the Riemann-Stieltjes integral. So, here we are going to see the upper and lower sums. Let P be the partition of the closed interval a comma b, and let capital Mk of f is the supreme of f of x such that x belongs to closed interval xk minus 1 comma xk, and small mk of f is the inframe of f of x, and the number up f alpha is sum of mk of f into delta alpha k, and LP f alpha is the sum of small mk of f into delta alpha k. So, here that up f alpha denotes the upper Riemann-Stieltjes sum of the function f with respect to alpha, and LP f alpha denotes the lower Riemann-Stieltjes sum of the partition P for the function f with respect to alpha. So, in the first theorem, assume that alpha increasing on the closed interval a comma b, then if p dash is finer than p, we have u p dash f alpha is less than or equal to u p f alpha, and L p dash f alpha is greater than or equal to L p f alpha. And second case, for any two partitions p1 and p2, we have L p f alpha is less than or equal to, L p1 f alpha less than or equal to u p2 f alpha. Now, we take a partition p1 which contains exactly one more point than p. So, then only we can say it is a finer one. So, let it be C. Let C be the point in the ith subinterval. So, we consider the upper Riemann sum for the given partition P1, that is up1 f alpha is summation of mk of f into delta alpha k, and k varies from 1 to n, also k not equal to I, plus m of, that is mi of alpha of c minus alpha of xi minus 1 plus m double dash of alpha of xi minus alpha of c. Here m1 is the supreme of f in the subinterval xi minus 1 comma c, and m double dash is the supreme of f in the subinterval c comma xi. From equation 1, we can write the upper Riemann sum up1 f alpha is less than or equal to sum of k varies from 1 to n and k not equal to I, mk of f into delta alpha k plus mi of f into alpha of c minus alpha of xi minus 1 plus mi of f into alpha of xi minus alpha of c. Since m1 is less than or equal to mi of f, and similarly m11 is less than or equal to mi of f, we can write the left hand side less than or equal to sum of mk of f into delta alpha k plus mi of f into alpha of xi minus alpha of xi minus 1. Thus, we can combine the above two and we write mk of f into delta alpha k plus mi of f into delta alpha k, and this mi also we use it to write that sum of k varies from 1 to n mk of f into delta alpha k, and this is nothing but up f alpha. Therefore, up1 f alpha is less than or equal to up f alpha. Similarly, we use it to write the infimum of f for the lower Riemann-Stieltjes integral, and we use it to prove that LP1 f alpha is greater than or equal to LP f alpha. Here it is an example for the upper and lower sum for the given integral. So, next we are going to see the definition for upper and lower Riemann-Stieltjes integral. So, assume that alpha is increasing on the closed interval a comma b. The upper Stieltjes integral of f with respect to alpha is defined as integral a to B bar f d alpha, infimum of U p f alpha such that P belongs to script P of A comma B, that is set of all partitions of A comma B. Similarly, the lower Stieltjes integral is defined as integral A bar to B f d alpha equal to supremum of L p f alpha, here for every P belongs to the set of all partitions of A comma B. So, here based on the above definition we are going to prove that I lower bar of f comma alpha is less than or equal to I upper bar of f comma alpha. So, here the statement given that alpha is increasing on the closed interval A comma B, then to show that I lower bar of f comma alpha is less than or equal to I upper bar of f comma alpha. So, by the definition, for any epsilon greater than 0 there exists a partition P such that U p f alpha is less than I upper bar of f comma alpha plus epsilon. Also, by previous definition of Stieltjes integral for the upper and lower integral, we can have I upper bar of f comma alpha plus epsilon is an upper bound to all the lower sums, and thus instead of the left hand side we used to write I lower bar of f comma alpha is less than or equal to I upper bar of f comma alpha plus epsilon, since epsilon is arbitrary. So, therefore, we can write I lower bar of f comma alpha is less than or equal to I upper bar of f comma alpha plus epsilon. So, here to prove the above theorem they have given some example. Alpha of x is equal to x which belongs to the closed interval, and alpha is given as an increasing function, and here we define f of x equal to 1 if x is rational, if it is 0 x is irrational, and here we are verifying the above condition. Next case, additive and linearity properties of upper and lower integrals. The upper and lower integrals has the many of the properties of the integral, and here the linearity properties say integral A to B bar f d alpha equal to integral A to C bar plus integral C to B bar f d alpha whenever A less than C less than B, and similarly we can write for the lower integral also. So, here the proof for the above two properties. First case, integral A to B bar f plus g d alpha, by the definition infimum of U p f, instead of f we can write f plus g comma alpha. Based on the definition we can write this, and this is nothing but infimum of U p f alpha plus U p g alpha, and hence we use it to write, we can split these two, and instead of these two we can write the integral, and therefore we have obtained the integral A to B bar f plus g of d alpha less than or equal to integral A to B bar f d alpha plus integral A to B bar g d alpha. So, similarly we can prove the second condition for the lower integral also. The next, Riemann's condition. Riemann's condition states that if f satisfies, if you want to say f satisfies the Riemann's condition with respect to alpha on the closed interval a comma b, if for every epsilon greater than 0 there exists a partition p epsilon such that p finer than p epsilon, which implies 0 less than or equal to U p f alpha minus L p f alpha less than epsilon. The theorem states that assume that alpha is increasing on the closed interval a comma b. Then the following three statements are equivalent. First one, f belongs to R of alpha on a comma b, and second one, f satisfies Riemann's condition with respect to alpha on the closed interval a comma b, and I lower bar of f comma alpha equal to I upper bar of f comma alpha. So, first we are assuming that alpha is an increasing function. We are assumed that f belongs to R of alpha on a comma b, and we are going to prove the second one, and based on the second we are going to prove third condition, and third condition gives the first one again. So, first let us assume that condition 1 holds in that is f belongs to R of alpha on the closed interval a comma b. That means integral a to b f d alpha exists on the given interval. So, assume 1 is true, that is f belongs to R of alpha on the closed interval a comma b. Then the second case we can easily prove that if alpha of a equal to alpha of b, and so that we can prove the above case alpha of a is less than alpha of b. By the definition of Riemann-Stieltjes integral given epsilon greater than 0 and there exists a partition P epsilon and Tk and Tk dash belongs to the closed interval xk minus 1 comma xk, and for any partition P finer than P epsilon, we can write modulus of summation of f of Tk into delta alpha k minus A is less than some epsilon. That is, here A denotes the integral a to b f d alpha, and since modulus of summation of f of Tk dash into delta alpha k minus A is less than epsilon by 3, and from these two we can write f of Tk minus f of Tk dash into delta alpha k is less than 2 epsilon by 3. And from the base we know that mk of f minus small mk of f equal to supreme of f of x minus f of x dash, such that x and x dash belong to the kth subinterval. For any h greater than 0, we can choose two interior points Tk and Tk dash, and so that f of Tk minus f of Tk dash is greater than mk of f minus small mk of f. And here we choose h as epsilon by 3 by alpha of b minus alpha of a. Now we consider up f alpha minus lp f alpha, and that can be written in the by the definition of u and l, that is summation of mk of f into delta alpha k minus summation of small mk of f into delta alpha k, and this can be written as f of Tk minus f of Tk dash into delta alpha k, and hence we have obtained finally that the up f alpha minus lp f alpha is less than epsilon, and thus we can write 0 less than or equal to up f alpha minus lp f alpha is less than epsilon. So condition 2 holds in that, and hence f satisfies the Riemann's condition. Now based on this second case we are going to prove the third one. Okay. So first let us assume that Riemann's condition holds, that is condition 2 holds in that. That means up f alpha minus lp f alpha is less than epsilon. Thus we can rewritten as that up f alpha is less than lp f alpha plus epsilon. By the definition we can write I upper bar of f comma alpha is less than or equal to up f alpha, and which is strictly less than lp f alpha plus epsilon by using Riemann's condition, and thus we have obtained that the LHS is less than or equal to I lower bar of f comma alpha plus epsilon, and we have I upper bar of f comma alpha less than or equal to I lower bar of f comma alpha plus epsilon. And since epsilon is arbitrary, so we can write I upper bar of f comma alpha less than or equal to I lower bar of f comma alpha. But we know that I upper bar of f comma alpha is greater than or equal to I lower bar of f comma alpha, and combining these two we get I upper bar of f comma alpha is equal to I lower bar of f comma alpha. Now we are going to assume condition 3 holds in that, and we are going to prove that A exists, that is integral a to b f d alpha exists. Now we claim that integral a to b f d alpha exists, and hence A can be expressed as integral a to b f d alpha. For that, by definition, given epsilon greater than 0, choose p epsilon dash such that up f alpha is less than I upper bar is less than or equal to f comma alpha plus epsilon. For all the partitions p finer than p epsilon dash, similarly we consider p epsilon double dash, and so that lp f alpha is greater than I lower bar of f comma alpha plus epsilon for all the partition p finer than p epsilon dash. Since the partition p epsilon is p epsilon dash union p epsilon double dash, then we can write the above. Therefore, from the assumption that I upper bar of f comma alpha is equal to I lower bar of f comma alpha equal to A, and hence A minus epsilon is less than SP f alpha is less than A plus epsilon. Thus we can obtain modulus of SP f alpha minus A is less than epsilon, and hence f belongs to R of alpha. So this shows condition 1 also holds in that. Next one, comparison theorem. Assume that alpha is increasing on the closed interval a comma b. If f belongs to R of alpha on the closed interval a comma b, and if f of x less than or equal to g of x for every x in the closed interval a comma b, then we have integral a to b f of x into d alpha of x is less than or equal to integral a to b g of x into d alpha of x. So, by definition SP f alpha can be written as sum of f of t k into delta alpha k. Here t k belongs to the kth subinterval, and this is less than or equal to f of t k into delta alpha k, and hence based on the given data that f of x is less than or equal to g of x, we use it to write summation of g of t k is less than or equal to g of t k into delta alpha k, and hence SP f alpha is less than or equal to SP g alpha, and thus the above inequality holds in that. Similarly, we can prove here also alpha is an increasing function on the closed interval a comma b, and if f belongs to R of alpha, then modulus of f belongs to alpha R of alpha on the closed interval a comma b, then we are getting the inequality modulus of integral a to b f of x into d alpha of x is less than or equal to integral a to b modulus of f of x into d alpha of x. So, from the definition of capital Mk of f and small mk of f, we can write that the difference between these two is the supremum of f of x minus f of x dash. Also, we know that modulus of f of x minus f of y is less than or equal to modulus of f of x minus f of y, and hence this is nothing but mk of modulus of f minus small mk of modulus of f is less than or equal to capital Mk of f minus small mk of f, and hence we can obtain the form that mk of modulus of f into delta alpha k minus small mk of f into modulus of f into delta alpha k is less than or equal to summation of mk of f minus small mk of f. That means up f alpha, that is up of modulus of f comma alpha minus LP modulus of f alpha less than or equal to up f alpha minus LP f alpha, that is less than epsilon, by using the Riemann's condition. So, this shows that modulus of f also belongs to R of alpha, and thus here the given data is f of x is less than or equal to g of x, and based on this we can write the inequality integral a to b f of x into d alpha of x less than or equal to integral a to b g of x into d alpha of x. Now, we replaced f of x modulus of f of x in the place of g of x, and hence we have obtained that modulus of f of x integral a to b d alpha of x is less than or equal to integral a to b f of x into d alpha of x. Next theorem states that if alpha is increasing on the closed interval a comma b, if f belongs to R of alpha on the closed interval a comma b, then f square also belongs to R of alpha on the closed interval a comma b. By using the definition, we use it to write capital Mk of f square is nothing but Mk of modulus of f the whole square, and similarly for the lower Riemann-Stieltjes also. So, hence we can show that whenever alpha is increasing on the closed interval a comma b, and if f belongs to R of alpha, then f square also belongs to R of alpha. Theorem 4 states that alpha is increasing on the closed interval a comma b. If f belongs to R of alpha and g belongs to R of alpha on a comma b, then the product also belongs to a comma b. So, in the previous theorem we have shown that f square belongs to R of alpha. So, instead of f dot f, here we are having f dot g, and thus f dot g also belongs to R of alpha. So, again the functions of bounded variation, that is integrators of bounded variation, since f is a function defined on the compact interval and p be a partition of the closed interval a comma b, and delta f k is nothing but f of x k minus f of x k minus 1, and k varies from 1 to n. Then f is said to be a function of bounded variation if there exists a positive number m such that summation of modulus of delta f k less than or equal to m. Here is an example for this one, and here f of x equal to x in the closed interval 0 comma 3, and delta f k is defined as f of x k minus f of x k minus 1, first delta f1 and then delta f2 and up to delta f3, and finally we are having this is less than or equal to 4, and this is a function which is a function of bounded variation. Then total variation, here this is a total, if f is a function of bounded variation on a comma b and summation of p equal to summation of modulus of delta fk corresponding to the partition p of a comma b, then the total variation of f on the closed interval a comma b is a number vf of a comma b, which is supremum of summation of p, and p belongs to the set of all partitions of a comma b. For a constant function, the total variation of a comma b is 0, and a function f is said to be a function of bounded variation if f can be expressed as the difference of two continuous and monotonically increasing function, and here we have proved this already, and based on this we can prove the same. And next theorem states that alpha be a bounded variation on a comma b and assume that f belongs to R of v on a comma b. Then we have to show that f belongs to R of alpha on every subinterval c comma d of a comma b. So here we are considering a subinterval in the given closed interval a comma b, and based on the total variation, v of x here denote the total variation of alpha on a comma x, and a less than x less than or equal to b, that is v of a equal to 0. Therefore alpha is a function of bounded variation. We use it to express alpha as alpha equal to v minus of v minus alpha. Here v and v minus alpha both are increasing functions on the closed interval a comma b, and by a theorem already we have proved that the difference of the two increasing function is also an increasing function, and hence this proves that f belongs to R of v and f belongs to R of v minus alpha, and thus f belongs to R of v on the closed interval c comma d, and same like that f belongs to R of v minus alpha on the same closed interval c comma d. Thus this shows that f belongs to R of alpha on the closed interval a comma c comma d, that is f belongs to R of alpha on every subinterval of the closed interval a comma b. Next theorem proves that assume f belongs to R of alpha and g belongs to R of alpha on the closed interval a comma b, where alpha is increasing on the given interval a comma b. So here define capital F of x and g of x as given, and then we want to show that small f belongs to R of g and small g belongs to R of f, and the product f dot g also belongs to R of alpha, and we have the given integral as integral a to b f of x into g of x into d alpha of x equal to integral a to b f of x d into g of x equal to integral a to b g of x into d f of x. So the above theorem is an application of theorem A, B and C, and hence we can prove this based on the above one. Since f belongs to R of alpha and g belongs to R of alpha on the closed interval a comma b, and thus already we have seen f square belongs to R of alpha. Similarly here fg belongs to R of alpha, and we can write the definition SPFG based on the given defined function capital G, and hence we can obtain the required form, that is integral a to b f of x into d g of x equal to integral a to b f of x into d f of x, and that is equal to integral a to b f of x g of x into d alpha of x. And next, the sufficient condition for the existence of Riemann-Stieltjes integral. The sufficient condition is if f is continuous on a comma b and alpha is of bounded variation, then f belongs to R of alpha on a comma b, and based on the upper and lower integral, that is up f alpha and LP f alpha, we can prove the same in this, and hence f belongs to R of alpha, and this is the sufficient condition for the Riemann-Stieltjes integral. And based on the sufficient condition, here we are having a theorem that f is continuous on a comma b and f is of bounded variation on a comma b. And the necessary condition for the existence of Riemann-Stieltjes integrals are: alpha is of bounded variation on a comma b, the continuity of f is sufficient for the existence of integral a to b f d alpha. Then by a theorem under step function, the integrators a to b f d alpha can be expressed as f of c into the difference of the right and the left hand derivative of c. We found that when alpha is a step function, then f can be defined quite arbitrarily in the closed interval a comma b, provided only that f is continuous at the discontinuities of alpha. So, the next theorem tells the necessary condition that assume alpha is increasing on the closed interval a comma b and let a less than c less than b, and further we assume that both f and alpha are discontinuous from the right at x is equal to c. That is, we are assuming that there exists epsilon greater than 0 and for every delta greater than 0, the values of x and y in the interval c comma c plus delta, and for which modulus of f of x minus f of c is greater than or equal to epsilon and modulus of alpha of y minus alpha of c is greater than or equal to epsilon. Then the integral a to b f d alpha cannot exist. This integral also fails to exist if alpha and f are discontinuous from the left at c. So, this is the necessary condition for this. So, to prove this, we consider a partition P containing a point C as the point of subdivision, and C is the left end point, and form UP f alpha minus LP f alpha, which is nothing but the sum of capital Mk of f minus small mk of f into delta alpha k. And by the definition, we can write this as the left hand side is greater than or equal to mi of f minus small mi of f into alpha of xi minus alpha of c, and every term of equation 1 is greater than or equal to 0. Here c is a point of discontinuous from the right. We can choose alpha of xi minus alpha of c greater than or equal to epsilon, and by the given data we know that capital Mi of f minus small mi of f is greater than or equal to epsilon, because since here f is discontinuous from the right at x is equal to c, and thus it is discontinuous. We can write UP f alpha minus LP f alpha is greater than epsilon, and hence UP f alpha minus LP f alpha is greater than or equal to epsilon, and thus integral a to b f d alpha does not exist. So, by the similar proof, we can prove that integral a to b f d alpha does not exist when x is a point of discontinuity at c from the left. Thank you.